Hello and welcome again to my Physics Video Lecture Supplement series. In today's video I want to talk a bit about ultimate strengths of material and basically breaking things. Actually, I just want to work a simple example just for the fun of it that involves a superhero, and this superhero decides that he is going to punch through a 10 centimeter thick piece of steel with his bare hands. And in order to do this, I actually want to work this problem through and find out how much force does he need to apply in order to break this piece of steel, and then what happens to him after he actually punches the material. So furthermore, I want to actually work this, the first part, through two ways. One is the wrong way, and the other is the right way. And the reason why I want to do that is to highlight a maybe common mistake that somebody would make coming into a problem like this. So let's say that we have a piece of steel, and it is 10 centimeters thick. And our superhero comes up and punches it. So his hand kind of collides with it here and punches out a piece of this material. And let's say that this is steel, and that the failure strength, or the ultimate strength, which I'm going to use an S to represent, is 250 megapascals. That's kind of a common strength of steel that I've seen in looking around online for how strong steel is. It kind of varies from a low of maybe 200 megapascals to, I've seen some people claim that they've made some tempered steels that exceed 300. So I'm going to go with kind of a median there, 250 megapascals. And the other piece of information we need to know is how big is his fist. So I'm going to take his fist to be roughly a rectangular cross section. We'll say that the fist can be approximated as a rectangle with width of about 8 centimeters and length of about 15 centimeters. So the cross-sectional area of his fist, therefore, is 8 by 15 is about 120 square centimeters. And that brings me into what is the wrong way of solving this problem. So regardless of what you do, you should know that this number right here, this ultimate strength, 250 megapascals, is how much force per unit area can the steel take before it breaks. So whether you do it the right way or the wrong way, you should be able to at least start off noting that the force divided by area needs to be exceeding the strength of the material. So let's look at the wrong way of doing it. In the wrong way, what we do is we say, well, he has a fist that is 8 by 15, so the area of his fist is 8 centimeters times 15 centimeters. And so we get a total area of 120 centimeters, which is 1.2 times 10 to the minus 2 square meters. So having done that, then the next step would look like force is area times strength. And so, therefore, the force should be greater than or equal to 250 megapascals which is 2.5 times 10 to the 8 newtons per meter squared, times 1.20 by 10 to the minus 2 meters squared. And so we would come out with a force of at least 3 million newtons. Now that sounds like a lot of force, and for a gut check, those 3 million newtons seem like it could maybe break through a thick piece of steel. Well, without any physical intuition to this, sure, that sounds like a lot of force. But there's a problem here that hopefully those of you who are watching have caught. And what that problem is that nowhere in this calculation do I take into account the thickness of this beam of steel that he's punching through. So hopefully you have at least enough physical intuition to realize that a thicker beam should require more force to punch through than a thinner beam. That is sort of common sense knowledge. You know, for example, that if you take a thin twig, you can snap it more easily. That's still a shear force. You can snap it easily or chop through it easily than if you have like a log that's a little thicker. So something is wrong here. What we've done, and where the mistake lies, is that we use the area of his fist to represent the area in this equation, and that's not the right area to use. What this basically does when you use the area of the fist is it's essentially equivalent to saying how much force would he need to apply on a steel rod or steel bar, which has the same area cross-sectionally as his fist, such that when he punches it, it buckles. So it breaks, but it breaks from compression, buckling, rather than shearing, punching a hole through it. So the right way to do it involves figuring out not the area of his fist, but rather the area parallel to the direction that he's punching of the steel. So what that really means is that he's punching out something that looks like this. Piece of steel that is maybe has some cross-section like this. He's punching this way into it, so we need to find the area that is parallel to the direction that he's actually applying the force. That's what a shear means. It means that you're looking at area of the object parallel to the direction that the force is being applied. So forgive my really awful drawings here, but that basically means we need to find the area of this side, the area of this side, the area of that side, the area of the side behind this figure, this three-dimensional figure. In other words, we need the lateral area of this chunk. So this lateral area, basically the width is here, that's that 8 centimeters. The length is here, and then this direction here gives you the height. So this is the right way. So the real area is going to be the perimeter of this cross section. In other words, the perimeter of his fist times the thickness of the steel. So now we actually are taking that thickness of steel into account. So the perimeter here is going to be width plus length plus width plus length. So twice width plus length times the height. So the actual area that you end up getting, rather than being 120 square meters, is more like square centimeters. Excuse me, is more like 460 square centimeters, or 0.046 meters squared. Now we can use this equation, because this equation is actually right. Now we use force is equal to area times strength, which tells us that force is equal to 0.0460 meters squared times the 250 megapascals. And so that gives us the actual force needed to punch through this piece of steel. So that total force, therefore, is actually equal to 1.15 times 10 to the 7 newtons, or 11,500,000 newtons. So it's an entire, almost order of magnitude greater than the force we got doing it the wrong way. And you'll notice that this thickness is a component of this force. It comes into the force through this area. It means that if you make the block thicker, then you need more force, and if you make it thinner, then you need less force. Basically, what's happening is that when we punch a hole in it, you're getting a shearing of layers in the part that's covered by his fist. These are basically sliding against the rest of the metal that's not covered by his fist, hence a shear force. So the other part of the example was what happens to the superhero once he punches this hole into this this steel. So suppose that your hero has a mass of 100 kilograms. That basically means that he would weigh 220 pounds. So he's a pretty big guy, but he's not, enormous. And basically what happens is when he punches this metal, this piece of steel, a force is applied back on his fist, a force equal to the force that he punched with. So let's say that he delivers the punch over maybe 0.1 second time. Maybe that's about the right length of time for a punch. Then that means that we can figure out what his recoil velocity is going to be, or his recoil speed. The velocity part is that it's a recoil. He moves away from this thing that he's punching. So you can figure out that based on whatever his initial speed was plus the average acceleration times the time, where the average acceleration is the average force per unit mass. So that's going to be 1.15 times 10 to the 7 newtons divided by 100 kilograms. So his average acceleration is 1.15 times 10 to the 5th meters per second squared. So assuming that he doesn't black out under this, I guess superheroes get to have some superpowers like being super tough. He still has this extreme recoil acceleration. So even if the initial speed is 0, even if he's just standing there when he takes that punch, this final speed is still going to be this acceleration times 0.1 second. So that's 11,500 meters per second. So that's a pretty high recoil speed. I mean, that's many times over, many hundreds of, almost 100 times the speed of sound. So I imagine that the sonic booms from this guy being launched backward would probably deafen anybody standing nearby. And furthermore, he maybe would land somewhere on the far side of the Earth, or more realistically, depending upon the angle he's punching at, he might be going into orbit. So apparently superheroes have more superpowers than they list in the storyline. So that's all for today, and thank you for watching.